exam outside the class time. If anybody has any other problem, please see me right away after class today. Now I have one good news for you and one bad news. So the good news is that as you all know, I'm writing a book on the subject. So many of you who've come to my office hours have seen these chapters and have asked me if I can share the chapter with you. I've written to the publisher to ask them if I can get permission, because these are all copyright, and if I give it to you, I will lose the copyright. So I've written to the publisher and they have given me permission to give you a copy. But now that's the good news. So the bad news is the only reason I can give you the copy is that you're supposed to give me feedback. And that was what I convinced the publisher, that the students will give me feedback, and so I will have something to justify giving these copies away. So what I have to do now is, on a first come, first served basis, I need 3 volunteers to review each of the chapters. You can't raise your hand, right? I can't do it. But I need 3 volunteers. I'll be giving you 2 chapters, chapter 2 and chapter 3. Okay, so I need 3 volunteers for chapter 2, which is on the chapter 2 is all on X-rays using the atomic structure, and chapter 3 is on bonding and structure of solids and all the techniques that come from that. So each of these I need 3 volunteers, and to make sure that you will turn it in, because I have to show the publisher that this has been done. Okay, so for that I'm going to give 5 bonus points for the one who volunteers and if they do it. And there will be minus 5 points if you don't turn it in. Okay? So there'll be 5 plus if you turn it in within a reasonable time, let's say 3 weeks or 4 weeks. And if you don't turn it in, you sign up and you don't turn it in, you'll have minus 5 points. What's that?
So only 3 people can read the book?
Well, no, everybody will get a copy. I will send a PDF file to everybody.
Okay.
But that is 3 people. I don't do anything selectively for the class. But 3 people who volunteer will get 5 bonus points, and they also take the negative. If they don't turn it in, minus 5. Okay, so it's fair across the board. It means you have to read it carefully, catch all the typos, all the mistakes that are there. And if something is not clear, you have to let me know this is not clear, this needs to be changed, or whatever. So you have to give me substantial feedback on that. That was the agreement with the publisher. Okay? Because I can't just randomly give this out, because I will lose the copyright. But if I can give it to people to read it and give me feedback, that's perfectly legitimate. So I'm doing it to the whole class. You guys are going to be reading this and giving me feedback. And I have a mechanism to make sure that if I'm asked by the publisher, here are the feedbacks, right? Because the copyright is very serious business. Okay, so after talking to you and a couple of other people, I said, okay, let me ask the publisher how I can do this. All right? And so these chapters are quite extensive. They're almost 40, 50 pages. Then all that stuff that I'm talking about is outlined in detail. Everything is there, right? Plus, actually, the homework problems are really the problems at the end of the chapters. They're already there. So, how shall we do this? Do you want to see me just after class? Send me email? How do you want to do this? I need 3 for chapter 2 and 3 for chapter 3. And only if I have 3 volunteers will I send out chapter 2. If I have 3 volunteers, I'll send out chapter 3.
We're just doing email.
What? What's this? Are we hearing? How many people want to just see me after class?
I can't see it for class, but I volunteer.
Okay, 1, 2. How many? What's that?
A lot of people have class after this, so why don't we just volunteer now and then those.
Okay, let's just do volunteer now. Let's see how many want to volunteer chapter 2. Okay, so those 2 hands went up first, this one went up third. So you bring chapter 2. Okay? And 3 of you bring chapter 2. And then how many of you want to do chapter 3? 1 went up here, 2, 3. Okay, 1, 2, and 3 doing chapter 3. Alright? Please do your feedback independently so I get different viewpoints. So, let's just write your names down. So, 2, who's doing 2? Then 12. be Josh,
Alex.
Alex again, and
Eden.
Eden.
Yes.
Okay, so we have two, and if I can do this to chapter 4, when I finish chapter 4, I'll send you chapter 4. I'm going to do this so that it will be perfectly fair after you finish the homework. So I will send it each one after the homework is done. Okay, so we've already done 2, you've done the homework, and I don't want to benefit people who are reading 2 or 3 to help them with the homework 3. So I will do it as soon as the homework is done. Okay? So I just want to be fair, people, I don't want people to complain and all that stuff. Okay.
The
Yeah.
content for any midterm is we can actually.
I cannot give you 4.
Okay.
The 3, 4 is today. I cannot do 4, but I can. I'm really trying extremely hard to do what I can. So don't push me, because then I will resist totally. Okay. So please don't push me, because I'm working extremely hard to get you this. Okay. So don't push me. I'll do my best. If you push me, then I'll just put something and say sorry, can't do it, because I'm trying to do things I shouldn't be doing. So okay. So please be careful about that. So let's. What else? We have the homeworks covered, we have the exam covered. What else? Anything else? Any administrative stuff? Organizational stuff? Okay. Alright. So because we missed the class on Friday, we are a bit behind. So I will not give you homework today. I'll probably give you, let me see how much I get through today, and then I'll give you the homework. And then again, whenever if I give it to you on Wednesday, you have till following Wednesday. If I give it to you on Friday, you have it till following Friday to get the homework done. Okay? And then the exam will be the following Monday, so you will still have the time. I will hopefully finish chapter 4 this week. So after this week, whatever we finish this week is what is in your midterm. So you have 1 week to work on that. And if I don't finish on Friday, I'll definitely finish by Monday what I need to do for the midterm.
Sorry, you just said the midterm was on Monday, but in the email you said it was on Friday.
Sorry, the following Friday.
Okay.
Sorry, I keep mixing up the Friday and
Just
the
wanted
Friday.
to confirm.
What I'm saying is that whatever for the midterm will be done hopefully 1 week before the midterm.
Okay.
So that you have time to review the stuff and learn the stuff. The one do till the last day and then just at the midterm.
Okay.
Either Friday or Monday I'll finish, hopefully by Friday I'll finish the essential concepts. Okay. So we're going to start with crystallography today. We're going to switch. We've done diffraction. It's going to be a very quick review. So I'm going to do it on the slides, and then I will come back and I will talk about the more important concept that you would have to learn is really on reciprocal space. Learn how to manage or manipulate reciprocal space. So we're going to spend a little bit of time with reciprocal space. So the key ideas here are basically that you have crystallites. When you grow crystallites, you have unit cells that randomly nucleate, they grow together, and when they grow together, they have these defects around them, which we call grain boundaries. There are a number of things these things affect. What it affects is that, as you know, the X-ray diffraction depends on what we call the correlation length. So if the length of the crystal is long enough, the spots become narrower and narrower, or the X-ray peaks become narrow and hard. If the spots are, if the grain size is large, then it becomes, the correlation length is sufficiently large that you get a very narrow peak. And if the grain size is small, you get peak broadening. And what this tells you is that if later on we will see we have reciprocal space, each of these diffraction spots occupies some volume in reciprocal space. And if you change the shape of the crystal or the object, the shape of the diffraction spot or the volume in reciprocal space will change. So that if you have a three-dimensional object in space, they're occupying a very large volume in real space, this reciprocal space, the diffraction spot, the volume in reciprocal space will be a very small point. But if you change the shape of your object from three-dimensional object like this and squeeze it down in one dimension to make a film, then that reciprocal space object will no longer be a point, but it will be essentially a rod. Because in this direction, you are squeezing it down, and therefore it spreads out, just like it spreads out in a grain, as you change the grain size. This is a very important concept, because as we go into diffraction in thin films, in particles, using electron microscopes and so on, this business of the reciprocal volume, the point in reciprocal space, being just a point, it's no longer a point, just as you know in diffraction, when you have grain size, there is peak broadening. And so this reciprocal space, the point in reciprocal space changes shape. And in electron microscopy and so on, they're called REL rods. And we will talk about this later. It's called REL rods. I don't know why they call it REL, but they call it REL rods. So a diffraction spot, instead of being like this, has a character like this, because you're looking at a very thin object, and therefore perpendicular to that direction, just like you have peak broadening, this volume in reciprocal space broadens out in one direction. It's a very important concept, because this was really the most important feature that allowed the early experiments on diffraction, which showed that electrons or waves be possible, because they did it from a surface, and the surface, they didn't quite know what they were doing. They didn't have the exact diffraction condition, but since it was a surface, there was the reciprocal space changed, and they could get the diffraction condition, even though it was close but not exact. And so this is an important concept we will come to later on. So the grain size, so this grain size is an important thing in terms of various aspects of diffraction that we will see. Now, the second thing that we also, I mentioned already, is what we call the difference between long range and short range order. So what we have is short range, where each of these, the green ones which are silicon, have 3 oxygen atoms here, and they form a periodic array. So there is a long range order in this case, and you will get a signature of the long range order in a diffraction pattern. And that is what you normally see as diffraction. But a lot of material, I don't know how many of you saw it, just 2 days ago, there was a news about Apple filing a new patent. Did anybody see this? So they are going to make a backplate for your iPhone. This backplate for your iPhone is going to be made of an amorphous alloy. So they have this patent where they are going to make the backplate out of an amorphous alloy. Now when we say an amorphous alloy, what we mean is that there is possibly a local order, but it doesn't exist over the long range. So here it is the same thing. Each of the silicon has the 3 oxygen atoms. The local environment is preserved, but that environment does not extend over long distances. Okay? And so this would have what we call short range order, but will not have long range order. So the key points here are, in this one, it is long range order. And here is what we call short Now, there's another important thing that you will see is that long range order. I don't know why this keeps happening. So this long range order.
Doesn't the long range order one also have short range order?
It could, yes.
Okay.
Yeah, because there's a local order anyway, but that is not important in terms of this. But this one only has short range order.
Okay.
That's true. The long range automatically assumes that there is some short range. Now, I think I should just put this down. Okay, so this long range order, there's another important thing that describes this long range order. And this long range order is described by a parameter which we call the order parameter. Okay, so this is not relevant to characterization, but sometimes you are interested in order parameters. It is and in what other field do you see order parameter? Where you need to understand something about order parameter, something to do with material science. Have you done a course? I don't know if you've done a course on phase transformations. Yeah. So in phase transformations, the important thing in phase transformations is order parameter. So you have to determine an order parameter both experimentally to figure out. So if you go from water to ice, as you go from water to ice, you develop an order parameter that describes the long range order in ice. So many phase transformations require order parameters. And this is something that we always need to be able to measure what is the order parameter if you're trying to do phase transformations. So you can see with just this one simple slide, you can talk about many aspects of material science. All right? So then we come to the basics of crystallography. So crystal structures, we specify them in terms of unit cells. And in the most general case, the unit cell is defined by 6 parameters. The 3 unit cell dimensions and the 3 angles. And in the most general case where there is no relationship between these, in the most general case, we have the triclinic. Where A is not related to B, is not related to C, alpha is not related to beta, is not related to gamma, and they are not equal to 90 degrees. And that's the most general one. Then after that, we come to one of these, which is the monoclinic, where one of these angles is at 90 degrees. So it is one angle, one is perpendicular, the rest of it is in plane. And then you go on to hexagonal and so on. And the highest symmetry is the cubic case. Now, there is an important aspect if you take a crystallography course, that each of these crystal classes that we talk about, these Bravais unit cells, is defined by a key symmetry element that says if you have this symmetry element, it is this kind of a crystal structure. So typically, if you have a 4-fold symmetry, that is, you rotate here, you rotate here, you rotate here, you come back here. That's 4-fold symmetry. People assume that a 4-fold symmetry is characteristic of a cube. But if you did that, you would be wrong. Because the characteristic 4-fold symmetry could also be for a tetragonal unit cell. So you have a tetragonal unit cell, you have exactly 4-fold, except that one axis is longer than the other. But you still have a 4-fold symmetry. So the important thing in a cubic symmetry is actually sets of 3-fold axes along the diagonals. So if you take the body diagonal of the cube, you rotate it by that is along the 1, 1, 1 direction, you get a 3-fold symmetry. So you get 1, 1, 1, 1, 1 bar 1, and 1, 1, 1 bar. These are the 3-fold axes that go along the diagonal of the cube. That is the characteristic, because that automatically generates 4-fold rotations in 3 orthogonal directions. Anyway, this is just a little bit of crystallography. So when you look at crystallography, things get a little bit more interesting and complicated. But so often when we talk about cubic structures, we are looking, so if you're looking at diffraction patterns and symmetries, you are going to look for that characteristic 3-fold symmetry, the 1, 1, 1, which tells you about the cubics. Okay? You all know this, so I'm not going to belabor this point. And this is the same thing that is in a tabular form. Oh yes, there's one important thing, and that is what we call a primitive and a multiple set. The primitive says that you have essentially one atom per unit cell. So when we talk about any of these and we have these face-centered, body-centered, these are they primitive cells or multiple cells? They are multiple cells. They do not have, and for each of these, there is an equivalent primitive cell. Okay, so let us just look at these. So this is this, and primitive and multiple cells. So here's a lattice. Okay, and this lattice, that is your primitive cell. Why is it a primitive cell? Because each of these lattice points is shared by 4 of these. This is a 2-dimensional object, 1, 2, 3, 4. So that contributes 1/4, that contributes 1/4, this contributes 1/4, and that contributes 1/4. So the unit cell has 1 atom per unit cell. Now, there is your double cell. And you can create the whole lattice with that double cell. You can just repeat that double cell. So now you have 1 on the boundaries, 1 in the center. So now you have a double cell. Here's a triple cell. Now, there's your cube. That is what? What sort of structure is that? Face-centered cubic. If that is face-centered cubic, that's 4 atoms per unit cell. So that is a multiple cell. And so there is the equivalent unit cell or the primitive cell for the FCC lattice. That's a rhombohedron. And you can generate the whole thing with this rhombohedron as well. Okay. So what we are using when we say FCC, unit cell, we really are talking about not a unit cell, but a multiple cell. But we use the word unit, and because we already use the unit, we use the word primitive, so that we don't confuse the two. Alright, so there's your primitive cell, and that is the cell for so 4 atoms per unit cell, and that is the equivalent one. Okay, so we use to choose this thing and then you already know how to write the coordinates for the various atoms. Unit cell, always the origin is at 0, 0, 0, the center is half, half, half. Okay. So we are all on the same page. So just to make sure you know this, there is the unit cell. There are 2 positions within the unit cell. You draw this out, and you can see this is 1, and you know the coordinates, how to write the coordinates of this. Because we will need this, and I just want to make sure we review this so that everybody knows this. And then we also know how to write about directions, how to index the directions. So there's one direction. So let's say that's the 2 bar, 1 bar, and here's the other one. So you should know how to write the directions. 4T1, 1T2, it's 4 bar. And the same thing extends to 3 dimensions. So here's the units, here's the lattice. It's a triclinic lattice. Here's your direction 2, 3, 1. That's the vector. And you should be able to index all of this 0, 1, 0, 0, 0, 1, and so on. This all should be done. I'm just reviewing it so that everybody's on the same page. It's a cubic now, and then they're showing you different directions. Anybody has any questions about how these are indexed? This is from Kalaki, so you should have seen this before. So everybody's okay with this because I don't want to come back to this later on. Okay? Fine. Let's do this. Now, everybody's clear with lattice planes and Miller indices. I will do this again in a most general way. You may have or may not have seen it this way, but this is the most general way of doing Miller indices. So here, it's a triclinic again, X, Y, Z, random directions. They are different, A, B, and C are different. So there are these intersections for that. And this intercepts at P, Q, and R at 1, 1, 1. This is the most general way you can do it. This one is another plane that intercepts at 2, 2.5, and 3.5. And so the equation of this plane is written as X divided by P, Y divided by Q, Z divided by R is equal to some integer M. So you just multiply this, XQR, YPR, ZPQ is PQR, and therefore you get XH, YK, ZL is PQR. And if you do this in the most general case, we apply this to plane A, PQ and R are 1, so X over 1, Y over 1, Z over 1 is equal to 1, and therefore HKL is 1. So that's your index. Now for the second one, as you can see, it can be more complicated. So you get X divided by 2, the X-intercept, then Y divided by 2.5, Z 3.5. You multiply all of this by PQR, so 8.75, 7Y, 5Z is 17.5, but this needs to be an integer. So you have to multiply all of this by 4, so you get 35, 20, so the HKL is 35, 28, 20. So that's the most general, you will never fail if you index it this way. Okay, doesn't matter what coordinate system, what it is, you will never fail if you index it this way. This is the most general way of indexing. People just take shortcuts. You're welcome to do it, but this is the most general way of indexing. Okay, so H is 35, H 28, understood. You have a slide of all of this, so just very quickly. Okay, so one more mark this. Okay, the family of planes, so the symbol we use, this brackets is for one plane, this squiggly brackets for a family of planes. Okay. Now, the interatomic spacings is something else that we are always, so we have a family of planes. We're looking at, yes please.
So I'm wondering, you have X over Q plus Y over Q plus Z over R equals M, and then you multiply by PQR, so then what happens to M?
M is always an integer. We use the smallest one, which is 1.
Okay.
Yeah. So that's what we did here. We set it to 1, and then we just multiply it. You can set it to 2, you'll get a different, you'll essentially get the family, the next one.
Okay.
Yeah. Okay, good question. Anybody has any other questions? So please feel free to stop and ask questions, because that's the key point of this, okay? So the other one is that we are interested in the separation between the planes, because when we do diffraction, we really want the separation between the planes. And you probably have seen this simple equation which says A divided by square root of X squared plus K squared plus L squared, but that only works for a cubic symmetry. If you have any other crystal structure, this interatomic spacings have to be given in terms of these angles. So for a cube, you have seen this. And the tetrahedral, it varies a little bit. For orthorhombic, it varies a little bit further. And as you go to more and lower and lower symmetry, that this expression for the interatomic spacing changes. So when you work, when you're just doing the first X-ray course, you sort of generally stay here, because that's what you work with. But in real life, you've got to know all of these, and they're just simply telling you the D spacings in rest using the parameters of the unit cell. So it's just an expression that you need to know, that's all. And you can calculate the interatomic spacings. You'll do a homework when you do this, yes.
So you're saying we should be prepared to do this on the
I don't know what you should be prepared to do. You should be learning how to use other things. What will be in the exam is a matter of, it's a different matter. But you should be, when you are in real world, when you go as a material scientist,
yes.
You don't care about an exam. You have a material, somebody gives it to you, you should be able to analyze it.
Right.
And not all materials are cubic. In fact, there are a very small number of materials that are cubic. So you should be able to analyze that. That's all. And the way that you analyze that is by knowing how to write the interatomic spacing. Yes, please.
I guess on this topic then, I know you said no notes on the exam, but then are you going to give us like an equation sheet?
Yes. If anything that you need will be in the exam. I will not tell you what it is. So every equation that you need, in all my exams, all the equations are there. It's not a question about memory. But you should know what the variables are. I'm not going to tell you what the variables are. I will use the same notations as in class. You will not have any problem with that. I'll give you what you need. Okay. But you should know what the variables are. I'm not going to tell you what the variables are. Okay. So now again, lattice planes, Miller indices. That is the equation of the plane that we just did. And now you can see we write it as equal to C. And this is very important. What this slide is very important because we are going to talk about zone axis, something you may or may not have seen before. Okay. So then C is an integral and describes the entire family of planes, parallel lattice planes. Now, as you can see, for HKL we are 0, giving C equal to 1 describes the plane of the set closest to the origin in the positive XYZ direction. And if you set C equal to -1, describe the plane of the set closest to the origin in the negative direction. Now, if you set this equal to 0, represents the plane passing through the origin. Okay? Now you should be able to realize something that you already know. If you have a plane with XYZ, you will see that if you have from the origin, there will be some point on the plane XYZ. HKL, as you know, is the index of the plane. The reciprocal lattice of a plane is normal to the plane. So if you take the dot product of something that is normal to something in the plane, that should go to 0. So that is the reason why you get HKL, when we talk about reciprocal lattice vectors later on, but I'm just setting you up. So the XY, Y, Z is some point on the plane. HKL is the index of the plane that's normal to the plane. And if you take the dot product of that, you get XH, YK, ZL should be equal to 0 by definition. When we talk about reciprocal lattice, we will define it such a way. Okay. For the passing represents a point on the plane, HKL, and hence XYZ is a vector, also represents a lattice line lying on the plane from the origin. Replacing XYG by the mode, you will get, this is the general form that you will see later on. XYZ is replaced by UVW, U times H, V times K, these are because they're normal. Orthogonal. We'll talk about this later on. Okay, so now this is the important thing that you will see, that you need to understand. So, for two planes with the Euler indices H1, K1, L1 and H2, K2, L2, you can find a common line, UVW, that is common to both the planes. So if you have one plane like this, another plane like that, they're going to intersect along a common line. Is that clear to everybody? So there's always a common line which two planes will intersect. So line curve is given by, and you can find that line, there's your common line. So there is your line, there's one plane, there's the other plane. There's always a common line. And you can find this by taking the cross product. Okay? So vector product of these Miller indices. Now, we call this, you can have, once you have this, you can have another plane that is also shares that common line. So the plane, always this line, UVW, is a common line shared by all of these planes. So if you take this line, we call this line or the direction of this line as the zone axis. That means that for this line, what characteristics do these planes have with respect to that line?
All the atoms should be.
No, we're not talking about atoms, we're talking about Miller indices. So what would the Miller indices or the reciprocal lattice, we'll come to the reciprocal lattice vectors, but they are all going to be normal to this line. Each of this line is on the plane, so the reciprocal lattice will be normal to this line. And the reciprocal lattice are our diffraction spots, right? So if you take a diffraction spot, you have a common direction, and all of these planes will have diffraction spots orthogonal, but given by the symmetry in some form. Is that point clear? So that's what is called a zone axis. Now I'll give you an example now. So they all satisfy this. This is the zone law, and we'll talk about this later in detail. So here's a typical diffraction pattern for a cubic crystal. forget about the details within the diffraction spot. That's a spot, that's a spot, that's a spot. All of them have this 0, 0, 1 direction common. So this is the normal to this. And so each of these diffraction spots, the index of this spot would be orthogonal to this. So you take the dot product of this with this, it should be 0. So that's how you index a diffraction pattern. So that you take a TEM diffraction pattern, you get not like X-ray, you get all the diffraction spots. You need to index that. So when you have the zone axis, you know that, so this would be 4, 0, 0. So you take the dot product with 0, 0, 1, it's 0. This would be 2, 2, 0. You take the dot product with 0, 0, 1, that'll be 0. So all of these, the first criterion is that the dot product should be 0. That is all the spots that correspond to this specific zone axis. You're looking at the crystal along that direction. And you get all these planes that satisfy diffraction conditions. And you look at the plane in that direction. If you look at the 1, 1, 1 direction, there will be different sets of planes that will be perpendicular to the 1, 1. And that will also give you a different symmetry when you look along the 1, 1, 1. So if you look along the cubic, along the 1, 1, 1, this diffraction pattern will not have a 4-fold symmetry, will have a 3-fold symmetry. This is a little bit more advanced, and here you get this ring. We'll talk about this a little bit later. You're familiar with this part. You should also be familiar with this. So if you take, not all elements have, not all materials have just a single element. Most of the common materials have more than one element. And you have one lattice formed by one element, and then the other element occupies various sites in that unit cell. And the typical sites that they occupy are tetrahedral sites and octahedral sites. And here, this is an FCC. Here's the FCC are given by these black dots, and these open dots are the sites. What sort of site is this? This one here. This shown by this white dot. What sort of a site is that? Is it octahedral, tetrahedral? What is it? Octahedral site. You guys know how to calculate the size of this octahedral site? Right? You know that in the FCC, if this is the unit cell A, what is this length here? This phase diagonal. A squared plus A squared square root. So how much is that? That's root 2A. And root 2A should be equal to, if you're calling this the atom A, it should be equal to 4A. Radius, 4 radius of A. And then here we can calculate this length, and then we can see this would be 1, whatever this is, 1 of A, 1 of X, which is here, or B, and this one, and then you can relate the two, and you can calculate the radius ratios. You guys know how to do this for various things? I'm going to give you one homework problem on it. Make sure you can touch up on this. And the same way you do for the tetrahedral side. In this case, you know this length, but then this length, you know that this distance from here to here is 1/4. Okay? And that way you calculate what is the biggest atom here that can occupy this one. This is for the BCC site. This is the tetrahedral site for the BCC. This is the octahedral site for the BCC. The octahedral site, this is not distorted. It's not the distortion of my drawing. That is the real, the octahedral site in the BCC is squished out. Okay, so this height is different from this height. So, so this is a little bit squished out for the BCC site. And again, one should be able to calculate these sites, the sizes for these. This is something that you should know, and you should be able to calculate. Some of them are 0.22. It's very important because if you put an atom that is bigger than that site, it goes and occupies that site and distorts the lattice. And if it distorts the lattice, in some cases, it strengthens the lattice. You cannot have dislocation, movement easily. This is what Brian will be talking about. And for example, a classic example is carbon in steels. When you put carbon, it occupies sites which are smaller than the carbon atoms. And when the carbon goes and occupies these sites, it distorts the lattice. And it creates an inhibition for the dislocations to move. So again, all of these have real practical consequences that we need to understand. But what we're trying to do is we're trying to characterize it, we're trying to understand, we're trying to measure these things. Okay, so then this is something you should know. You all know about stereographic projections. This is really important. Again, I'm going to do this in one slide, so you just know a very quick review of stereographic projection. So the stereographic projection, you have a sphere, it's a unit sphere. You put your crystal in the center of the sphere. So put the crystal at the center of the sphere, and for each of the planes that is of interest to you, you take the plane and you extend the normal till it hits the surface of the sphere. You take this normal, it hits the surface of the sphere. You position yourself on the south pole. And you draw a line from the south pole to the point where that extension hits the surface of the sphere. And that where that line intersects this equatorial plane is your stereographic projection. The whole thing is a mouthful, but that's the process. You could use this, either the equatorial plane, or you could put a plane on the north pole and extend this line. That is also done. It's called the nomic projection. But they give you almost essentially similar information. You have to just either use the equatorial plane or a tangential plane on the north pole. One is called stereographic projection, the other one is nomic projection. But the idea is essentially the same. The reason we do this, does anybody know why we take the trouble of doing stereographic projection? Just because we want to make life hard for ourselves? There must be a good reason. Why do we do it? Does anybody make a guess?
That's what you see when you do, what is it, Lowry diffraction?
Yeah, but why? But there's a fundamental reason why we do. Yes. Exactly. We have three-dimensional objects. We are trying to represent three-dimensional objects on a two-dimensional page. So we are taking three-dimensional symmetry and we are trying to always put it on a two-dimensional page. So we have to find a mechanism that everybody understands, that everybody agrees. That's how we do the representation from three dimensions to two dimensions. So that is the key idea of it. That's why we insist on using the stereographic projection, because we are always trying to represent a three-dimensional object on a two-dimensional page. This is, you've seen things, you've seen the wolf net, and you know how to use the wolf net. If not, go look it up. I'm not going to revise how to use the wolf. It's in my notes, eventually you'll get it, but you should know how to use wolf nets. Basically, how you use wolf net to measure angle between planes, how to orient stuff using the wolf net, and things like that. You should know how to use the wolf net. You should have already done this in the previous course. Okay, the last bit I want to cover today. Today is really a review. I just want to make sure everybody's on the same page on everything before I start to move ahead with this. So today I'll finish the sort of review of crystal structures, crystallography. I have 5 more minutes so I can finish what I need to do now. And then the next class, I'm going to talk about reciprocal lattice. I'm going to spend the whole class just making sure you all understand what a reciprocal lattice is. And then on Friday, I'll do diffraction. Okay, that's the plan for this week. Hopefully I'll be done by Friday, and then after we do one. So I will probably give you the homework this Wednesday. So you can start the homework on Wednesday, and you'll be due next Wednesday. You'll have the exam on the following Friday. If you turn in the exam on Wednesday, I'll give you chapter 4 on Wednesday, so you'll have it for your exam.
Yay!
Okay, so we'll work it out. As long as I get it done and I can meet all the rules that I'm subject to, we'll have chapter 4. Okay, I still haven't finished. I have 5 more minutes. So the important things that you should know are defects. And we are often interested in characterizing defects. The defects are there are 3 kinds of defects. We call them point defects, line defects and plane defects. The point defects, as you know, are two kinds. There's interstitials, so there is an atom occupying an empty space. And those interstitials, or you can have a vacancy where an atom should be. But these defects are very, very, very difficult to characterize. I can keep adding more values because they're really hard to characterize. So there are only one or two very good ways that give you some idea of these defects, and that is the method is positron annihilation. We don't have the physics background to go through that, so I'm going to skip that. Okay. The other defects that you probably know are the dislocations, edge and screw dislocations. Here you have the extra half plane here, and you know the Burgers vector, and the direction of the Burgers vector and the direction of the dislocation is perpendicular here. You have a screw dislocation where they are in the same direction. Typically, dislocations look like this in linear micrographs. And you have a way to look at to determine the Burgers vector using such micrographs. If you set a diffraction condition, which you use a reciprocal lattice vector that is perpendicular to the Burgers vector, that is G. So we have what we call, these are the classic G dot B experiments. So these are the classic G dot B experiment. This is equal to 0. So what happens if you set up this kind of diffraction condition, where the G, that is the reciprocal lattice in the diffraction pattern in the TM, is perpendicular to the Burgers vector, then that dislocation will suddenly go away from black, the contrast will go away. That's how you identify the Burgers vector, the rest of the diffraction. Okay? So when we talk about TM, we'll talk about this. And then that's what they look like. And these are the grain boundaries. And you can have grain boundaries, where this is one kind of grain boundary, as you can see. There's a dislocation. These are set of grain boundaries where the two grains are related to each other and they are separated by arrays of dislocations. If these dislocations are edge dislocations, you have what is called a tilt boundary. That is, the two grains are tilted with respect to each other. If this array of dislocations are screw dislocations, then this grain boundary is called a twist boundary. So the two grains are twisted when they introduce screw dislocations as they go from one to the other. So these are things that one needs to characterize. You need to be able to understand whether it's a twist boundary, a tilt boundary, whether there is a grain, whether it's a screw dislocation or an edge dislocation. I'll just forget this. That's about it. So I have sort of given you everything that you should know from background today. So if there is any question, please ask me. And then, either come to my office hours today or come and see me. Or ask the TA. Your homework is due to